Hello and welcome to part 2 of my Displays and Monitors 101 series. This video talks about the types of LCDs, including various panel technologies such as TN, VA, and IPS, as well as various backlighting technologies, including CCFL, LED, as well as MiniLED. If you haven't seen part 1 yet, part 1 talks about LCDs versus CRTs, as well as the fundamentals of displays. It's linked in the description down below. And part 3, which you can watch right after this one, talks about OLEDs as well as self-emissive displays. Without further ado, here's part 2.
The second thing I mentioned was the LCD types. Now, these are a little bit more interesting because there's lots of different advantages and disadvantages and trade-offs that you make depending on the type of LCD that you use. So historically, you just had like TFT LCDs, thin film transistor LCDs. And then these days, you won't see plain old LCDs. You'll see one of a couple types. So on most cheap displays, you will see what are called TN panels. TN standing for twisted pneumatic. Or no one ever calls it that, so we'll just keep it with the acronym. You will see VA panels, VA standing for vertical alignment, and you will see IPS panels, which stands for in-plane switching. You will see a lot of what they call IPS-like panels because the actual IPS word itself is a technology is patented by LG Display. So they're the only ones that can use the official branding IPS, but you'll see lots of IPS-like. So you'll see, for example, HWVA, which stands for hyper-wide viewing angle. That's what I believe AU Optronics calls their IPS equivalent. So there's a lot of these IPS-like things. Samsung used to call theirs PLS, or plane-to-line switching. Again, fundamentally the same thing as IPS, same advantages, same disadvantages, just slightly different ways of doing it to skirt the patents and not have to pay LG. So between these, what are the key differences? Well, they all work by changing the polarization of the crystals so that to either allow light to pass through when combined with the polarization filter or not allow light to pass through. Not all of them technically need polarization filters. There's a lot of fine details there about how exactly they're manufactured, but we can talk about the key differences and the key advantages and disadvantages of each. Are you about to fall asleep? So let's do a quick comparison of these various types. So pros and cons for TNs. And again, remember that these are all subtypes of LCD and, well, what they call LED displays. So that's, you can have an LCD with an LED backlight with one of various LCD types. So TNs, well, the first thing is that they're really cheap to manufacture these days, which of course means that they make their way into all sorts of devices where maybe they're not even the best type, but they're so commonplace that I have to mention it. That's why you see them everywhere. The second thing is they have relatively fast response times. And finally, a third benefit is that they tend to have lower motion blur. Because essentially, original LCDs would take some time to transition between these orientations. And of course, that transition means that you're going to, if I'm like moving a cursor, by the time you get to see the cursor, that's what I mean by reaction response time is, it takes time for the crystal to turn vertical or horizontal, vice versa. And you see that as like image fading in, fading out when you move. Motion blur means that, well, that continues over time. So if I'm moving and like, if I have an application open on my screen and I'm, moving it around, that means that you kind of seeing the trails of that because it can't actually turn the pixels off fast enough. And that tends to be very annoying, especially for when there's moving objects for things like gaming or movies. So TNs very much help to reduce that compared to traditional LCD displays. So that's why they started to take over in the 2000s, right after like early LCDs, because they had much faster response and lower blur. So, of course, however, it's not magical. They do have notable downsides, and the biggest downside these days is they tend to have bad viewing angles. In fact, there's really easy ways to tell if you're on a TN display. If you look at the display from higher or lower, you'll see that the display gets too bright or too dark. So typically, these displays are calibrated to a gamma of 2.2. Think about gamma as something that's existed since the CRT days. It's literally represented by the symbol gamma. Represents the exponential factor of the curve because, well, it turns out it's a lot more efficient to transmit signals exponentially versus linearly, and the human eye see exponentially. So displays run, obviously, exponentially. And so these days, a typical gamma value of a display that you are aiming for would be a gamma of 2.2 in SDR mode. In HDR mode, you have stuff like PQ and whatnot that takes over instead. So if you look at a display from too high or too low, you will notice the gamma value essentially tends to shift, and the display will either get too bright or too dark to use, depending on your angle. So very bad viewing angles. So that's if you're going top-bottom, especially bad in the vertical axis. And if you're in the horizontal axis, you will typically see this being manifested as the display turning a greenish versus pinkish color when you look at it from the left or the right. Which one depends on more precisely on which subpixel layout it's using, but there's tests you can do online that will essentially allow you to look at an image. It's easy if you have like red, cyan alternating lines. You can tell if you have a TN panel. So color shift in the horizontal axis, brightness and gamma shift in the vertical axis. Really bad to look at if you're not straight on. The other bad thing about them, well, they're not really the best with colors. This has greatly advanced over the years, and not all of it is the fact that it's a TN. A lot of it tends to come down to the fact that they're used on cheaper displays. But given the low viewing angles and how often the color shifts when you're off axis, you're not going to get the best colors out of these. And essentially, they also don't have particularly good, well, they have okay, so I'll put it as a maybe. They tend to have okay black levels. Better than something like IPS, but not ideal. Definitely not something like a self-emissive. So I think that's the rough pros and cons of TN. So TNs, again, to this day, you will see them on lots of cheap computer monitors or on laptops especially, even though they're not particularly compelling. Let's move on to VA. VA stands for vertical alignment. It's used typically these days on mid-tier displays, or more specifically, it's very common on a lot of TV as well as IPS. VA and IPS are typically what you will see in most premium-ish displays. VA on the slightly cheaper end, IPS on the slightly more premium end. You'll see MiniLED. MiniLED is a backlight type. I'll talk about that when we get the backlight types. Newer, so I didn't really include it on the CCFL LED because it's not as major. As I said, very common on TVs as well as mid-tier gaming displays. VAs are, well, the first advantage is better colors than TN. And just so I don't upset my audience, I'll fix the spelling of the word color here. So they have better viewing angles. Again, not the best. IPS is typically better from both the color gamut stance as well as the viewing angle stance. But this is a market improvement over TN. And we'll make a comparison chart maybe down here or something. You also get much better black levels. In fact, you'll get some of the best black levels in any display, except OLEDs, of course. You get the best black levels between the various types of LCDs. So when you're looking at it spot on, a dark scene will actually look dark typically. Unfortunately, they still have some color shift. So not the best viewing angle. Another plus actually is that they're typically used on a lot of these curved displays because the panel type is a lot easier to implement into curved displays. You will see some IPS panels on curved displays, but it's typically very rare, and VA tends to be the main kind there. So I would say that's pretty much a rough overview. They also are better than IPS in terms of response time. So not as good, but we'll put that as a question mark. The response time and motion blur tend to be okay.
So I wanted to give you an in-person demonstration of just how bad the smearing issue on VA can be. So on your left, you are seeing a 27-inch IPS 4K display, 60 Hz. On the right, you are seeing a 1440p 165 Hz VA panel. In the background is a dark gray terminal and a black MPV window, and you can see just how much smearing occurs when I move the MPV panel in front of the dark gray terminal. On the IPS, this looks perfectly fine, even though it's only running at 60 Hz, so it might not look super smooth. You don't get any type of smearing or trails behind it. However, on the VA panel on the right, you can clearly see it almost looks like you have the Windows cursor trails turned on, and you can see it's very smudgy and smeary.
You can also drive the refresh rate all the way up to 240 Hertz, and typically VA panels will be fine. TN you can drive all the way up to 500 or so these days before the panel starts to completely freak out. So okay response times, and it kind of falls as a good middle ground between TN and IPS. Now, I guess I've been talking about IPS for a lot, so what is IPS? IPS is in-plane switching. It's what I would probably consider the best LCD type. So IPS displays tend to have very good colors. They have the best viewing angles of the types of LCDs. They have a couple of fundamental downsides. The first is that IPS panels tend to have experience something called IPS glow. And what that means is that dark scenes won't typically look very dark. If you're looking at a perfectly black screen on an IPS, it's not the same thing as backlight bleed. Backlight bleed is how much of the backlight makes it through when the panel is set to being opaque. So when it should be blocking all light, some of it will obviously make it through, between the gaps of the pixels and whatnot. IPS globes, if you look at it, especially if you're spot on, especially on the outer sides, you will tend to see it almost look gray instead of looking black. And that's a fundamental issue. You can't really change that. It's core to the technology. If you want low blacks, then you have to go VA.
So let me try to quickly explain IPS glow. IPS glow is the stuff you see here and here. So if I move the camera, you will notice that you never get very good contrast if I turn the lights off especially. This is not a light source that's behind me. This is something that is inherent to the panel type itself. So whenever you have a dark image, you won't actually be able to get very deep blacks because you will always have IPS glow. And the closer you are, the worse it will be. So you can see this part and this part right now just look very bright. If you sit far enough away, maybe that's not as big of an issue. If you're looking at your display during bright lights, that's also probably fine. Here's another IPS. This one's 1440p, and you can see the exact same thing where you will see, no matter where you look, the other part of the monitor will appear to be brighter, and that's just called IPS glow. If you're not on pitch black and you're on gray, for example, you won't experience this. So it's only really an issue if you're in a dark room. You wouldn't notice it if the room is pretty bright. And it's also only really an issue when you're looking at something really dark on the display.
But also, they don't have the very best response times. So as a result of this, you typically won't see IPS panels used for a lot of gaming displays. And this has improved over the years. You see technologies like rapid IPS or fast IPS. Everyone calls it something different. And you will see IPS used on gaming monitors these days just because the colors are so much better. How good? Well, on an IPS, you can typically get almost 100, you can get 100% Adobe RGB coverage. If you have a proper backlight type, which you will not be getting with any other display type. You can easily exceed 100% DCI-P3. Very good colors. This is why you will always see the content creation or content consumption monitors be IPS. So whether you're either like watching movies or you're editing for them, you will typically see IPS monitors in use just because they're much more color accurate. You can easily calibrate them versus TN. Much better viewing angles. So if you're looking at it off axis, colors still tend to look good. You can also easily get away with doing 10-bit or 12-bit color, so you get a lot more finer control. TN, you really won't see anything past 8-bit. 8-bit being, so you won't even see 8-bit. Half the time they'll be 6-bit. 6-bit means that, well, each pixel goes 0 to 64. And then it does dithering to try to get 0 to 255. And you can easily see banding on those displays. So that's something what's called bit depth. It's really a separate type, but it's kind of tied to this. You will see displays using 6 plus 2 bits. They call it 6 plus 2. When they say 8-bit, they typically mean 6 plus 2. That's 6 bits of actual bit depth. So that means that the pixels can show from 0 to 64. They have 64 shades of red, green, blue, which means in total, you don't get very many colors. You will see 8 plus 2 in use. 8 plus 2 these days is fairly common. Sometimes they'll be called 10-bit displays, and you'll also see like 10 plus 2. 10 plus 2 or like anything past 10 will typically only be for content creation. So they'll typically be exorbitantly priced because they know consumers aren't buying it. And if you're buying it, you probably have money. 8 plus 2 is what I would consider the good standard these days. I shouldn't write these so close because they're not actually tied to VA or IPS. So these days, 8 plus 2 is probably where you're going to be, but laptop screens and whatnot will still ship with 6 plus 2. It's fine. It's not great. If you look at a gradient, you will easily be able to tell these apart. If you're using 10-bit versus 8-bit color on the computer, the difference becomes very noticeable. You get lots of banding. But yeah, so between these, IPS is typically considered the best. Of course, what you're considering the best depends on who you are. If you're a tech person, you look at a screen for long hours, you probably want good colors that you can calibrate. So IPS tends to win. You're doing photo editing, video editing, IPS tends to win. You're doing gaming, I would still say buy an IPS monitor. Like, the response times have gotten fast enough where you probably don't need that slight boost that you would get from TN or VA. The exception being if you're buying a curved monitor. A lot of curved monitors these days, as I said, are VA. A lot of TVs, as I said, tend to still use VA because they don't want IPS glow. However, IPS can look good on a TV as well. So those are the 3 main panel types. So if we were to rank them in terms of colors, IPS is the best, gets 3 stars. VA gets 2 stars, TN gets 1 star. It's the worst, awful colors. If we're ranking for response time, it's actually the opposite. TN tends to win, VA is second, IPS is third. And basically, you can see where the trade-off is going. Response time, motion blur follows response time very closely. Color calibration accuracy tends to follow good colors, and same with viewing angles. IPS is best for best viewing angles, okay viewing angles, and awful viewing angles. There's one thing I didn't mention here, which is that these days you might have been hearing something called mini-LED. There's terms flying around like mini-LED and micro-LED. What are mini-LED and micro-LED? They sound similar. They're actually completely fundamentally different. Micro-LED is truly impressive. I've never gotten to see one, but it's supposed to be the next big thing. Micro-LEDs are very much like OLEDs. So I'll put micro-LED here. Mini-LEDs sound similar, but they're actually not exciting at all. Just like how the manufacturers pulled the scam where they started calling the same LCD displays LED just because there's an LED backlight. Mini-LED is just a backlight type. And let me be very clear to draw a dividing line here. Mini-LEDs are, well, basically what we've started doing is, I said that one of the fundamental downsides of IPS displays is that they're not very good at doing black levels. So, because there's always backlight that's always on, right? This thing here is always on, and you're just trying to block as much of it as possible. So how does mini-LED work? Well, basically, mini-LED is kind of tied to the concept of local dimming. You can have local dimming without using it. So let's talk about what local dimming is first. Local dimming basically means that historically, all the LEDs that you had back here were all tied together. So the whole backlight was either on or off. Of course, you can dim it, but the whole thing would act together. You can't turn one light on but one light off. The concept of local dimming says that, well, why do all of these lights have to be tied together? We should be able to control them separately. So if, for example, if there's a bright part of the screen here and this side's dark, well, to make the dark scene look dark, why don't we just actually turn the backlight off? Historically, this was done through something called dynamic contrast. Dynamic contrast looks at what's on the screen and then adjusts to backlight accordingly. So if in a movie, if you're in a bright scene, the backlight will be at 100%. If you're in a dark scene, it'll dim the backlight. Dynamic contrast tends to look bad because you don't really get dynamic range from it. If half the scene is bright, half the scene is dark, it just freaks out. Doesn't know what to do. Doesn't look good. You can see the backlight turning on and off. What local dimming does is basically take this, divide it into zones. So a typical display can have a couple hundred zones. And this way, basically, you divide it into a big grid. And so each zone acts like its own backlight. It looks at, hey, what is on my little section of the display? Is it something dark or is it something bright? If it's something bright, crank the backlight there. If it's something dark, turn the backlight there off. And that's essentially how local dimming works. Now, a lot of laptop and computer displays are edge lit. This means that the LEDs aren't actually behind the panel. Rather, the LEDs are embedded at the top and bottom, and they use a diffuser to try to get as even light distribution as possible from the top and the bottom throughout the whole plane. Now, of course, that means that then if my LEDs are only on the top and the bottom, as you see typically with display HDR400 displays, your local dimming is based on vertical bands. If it's bright on the top, dark on the bottom, they can't do anything. They can only do it in these vertical slices if the right half is bright versus the left half is bright. So that tends to not work as well. The problem with putting them behind is these LEDs are so large that you can only put 20, 30 of them before in the back of this plane. It also adds thickness. Also means that now I have to get rid of the heat back here. So on TVs, you would see it. On TVs, you could get a couple hundred dimming zones. With mini LEDs, it's literally exactly what the name says. We've taken the LEDs that we use in the backlight and we've made them smaller. So instead of being able to fit 100 LEDs back here, we can now fit 1,000 of LEDs back here. So with mini LEDs, you can go all the way to a couple thousand local dimming zones. And of course, that means that HDR and whatnot is going to look a lot more convincing because now we can more finely be oh, there's a bright thing here, there's a dark thing here. Now, a disadvantage of local dimming is, if you have a dark wallpaper, if your computer has a black background, and I have the mouse that's one bright spot, you will typically see a halo around it because, well, the LED behind the mouse icon has to be lit. Except the problem is, those were so large that you were lighting up like 10% of the display just so you could like see where the mouse is, and you ended up with these massive halos. So mini-LED helps to reduce that a little bit. You still get lots of haloing, especially if like you have a single bright dot like a mouse cursor on an otherwise dark display. But of course, for things like movies, that means you get a lot more convincing HDR. Now, typically, we can talk about display HDR, but HDR, that's a whole separate video I intend to make at some point in the future. Dolby Vision versus display HDR versus PQ versus, there's so many of these certifications and HDR modes, and they're all weird. Not all of them are the same. There's ones that are good, there's ones that are bad. But essentially, display HDR 400 means you can go up to 400 nits. That's a VESA specification. It's not a way of doing HDR. A way of doing HDR would be something AMD FreeSync Premium Pro versus which uses PQ curves. But yes, so for 400, you'll typically use top and bottom lit. But if you want to do any higher, you want to do like display HDR 600 or display like 1000, you will need to use mini LEDs. And you can get like display HDR 1000 even on LCDs. For example, the Asus ProArt displays. And yeah, that's one other benefit, by the way, because we have so many more of these LEDs instead of only having like a couple, like a handful, you can get much brighter displays all the way to thousands of nits. And this means that typically you can sustain it on the whole screen. So with OLEDs, we'll talk about it, but you'll only get that high brightness on a small fraction of the display. Whereas with this, you can sustain it over a much larger area because the power draw is known. We don't have to worry about burn-in. Oh yeah, burn-in. I said that there's a lot of burn-in with CRTs because the phosphors tend to wear out. With LCDs, while you can get some amount of burn-in, it's being greatly reduced over the years. You typically will not see it on most LCDs. You will see what is called image retention. Image retention is essentially like, think of it like non-permanent burn-in. This happens a crazy ton on my home monitor, where if you have say a text document open with like a Word document, like a white center part and like the dark theme outside of it, you close it, you open something gray, you will see the outlines of it. Typically, it happens more on the edges of a display. But the thing with image retention is typically it will go away after 15, 20 minutes, especially if you put something else. Now, if displays already tried to kind of mitigate it, right? Like LCDs don't run on DC. If they run on DC, they would burn in and die instantly. So instead, you see the display will actually flip the positive and negative ends of the LCD, just like how you would do like for fluorescent lights in order to not get the pixel to like wear out as easily. But you will still get some image retention, especially on newer displays that have lower quality control than the original LCDs did. It can be bad, but it's not. At least it's not as bad as burn-in. So that's what mini LED is. More backlight dimming zones. They go brighter. They have better contrast. Fundamentally, it's the same type of display. It's not self-emissive. Do not confuse it for micro LED. They're very fundamentally different. That's LCDs.
Thank you so much for watching part 2 of my Monitors and Displays 101 series. If you enjoyed this video, please consider leaving a like or subscribing to the channel. Part 3, which talks about display and self-emissive technologies, is linked in the description down below, and you can watch it right after this. Thanks so much for watching. See you next time.